Okay, so let's open up Geoda. Let's double click on it here. And again, we have the floating toolbar here. And the easiest way, if you've already been working with a shape file before, you can just click, and you see I've been working with basically the same one here multiple times, but I have a few copies of it. You can take the shape file part and you can drag it and drop it here if you want. And that opens up a little map of the regions that you're working with. I'm going to leave this file folder open over here so we can look at some of the weights matrices, look at their structure once we create them. So here's a little map with our regions of the counties of North Carolina and Virginia in the United States of America. So let's click on the W and we can create weights matrices, or we can load some old ones that we've made. So let's create 3 different weights matrices and see what the differences are. So let's create, say, a queen and a rook so we can see the difference between those, and then we'll do a distance-based weights matrix and we'll see if that has any impact whenever we calculate a spatial correlation, also called a Moran's eye. So let's click create here. So it's very easy to create weights matrices. So weights file ID variable. So this is going to be in the files when we save them. How does it identify the region that we want? In the United States, when you're working with counties, it's good to use FIPS. So I have FIPS and I also have FIPS2 here. I think they're actually the same thing. That was the variable we matched on in QGIS when we created this. So let's use FIPS code as the ID variable so we can identify these counties. And let's first create a queen. Order of contiguity. So 1 means only if you touch on a border or a corner directly are you going to be a neighbor. If you set this to second order contiguity, that would mean that, say, a neighbor of a neighbor is also going to be a neighbor of mine. That's what a second order means, right? So not only my neighbors are my neighbors, but neighbors of neighbors. So if you're a queen neighbor to one of my queen neighbors, you get the idea. Let's just leave that at 1 and let's click create. And let's save this here with this .gal file extension we were talking about before. And let's name this queen so we know that's the one. Weights file queen has been created successfully. Okay, so let's close this window. And now let's explore those neighbors a little bit. So let's click histogram. And this tells us how many regions have how many neighbors under queen contiguity. So we see that there are about, 17 or so here that have only 1 neighbor. So let's move this histogram out of the way and let's look at the ones who only have 1 neighbor. In Virginia, we have a lot of regions that only have 1 neighbor, because in Virginia they have not only counties, they also have these little independent cities, most of which are contained completely within a county. So it's the town that normally would be the county seat, what we would think of. They're independent cities that aren't technically part of the same county. So we have a lot of those in Virginia. And over here, we have these 2 regions that are attached over here to Maryland. So this isn't really an island, but we don't have the state of Maryland up here. And so this region only has this one as a neighbor. Okay? So let's bring back in our histogram. So a lot of these areas that have 1 neighbor, so I'm using this linking and brushing kind of idea here. About 25, 26, 27 have 2 neighbors, 3 neighbors, 4 neighbors, 5 neighbors, etc. And the region with the most neighbors has 11 neighbors. And so let's look at that region a little bit and see why it has so many neighbors. Yeah, so it looks like we have a lot of little counties, and I'm sorry this is really faded out here in Geoda, but yeah, you can kind of see. Let's click back here. We can see that this region does indeed have a lot of neighbors that are touching it or meet at a corner. So that's a good way to understand our neighbors and do they make sense? Especially these ones that have only one neighbor, you'll have to think about for your particular model, does this make sense that these independent cities would only be neighbors to the surrounding county? Does it make sense that these two little regions over here would only be neighbors to each other? Maybe there's a ferry that connects this region to some of these counties over here in Virginia. And maybe not. So we might want to build that in to our network some other way than defining queen contiguity. So another thing we can do is we can look at a connectivity map. So click connectivity map, and this lets you just move your mouse cursor over the map and you can see who are the neighbors to whom. And so we can see that region that has 11 neighbors there, and it shows us which ones are the neighbors. And if we go over here and we highlight this region on that little island, we see the one neighbor, right? So this kind of helps us visualize what these neighbors, that if we're row standardizing, which areas are going to be the weighted average. So again, if you only have one neighbor, just the surrounding county is going to be the only thing that influences you. And in many cases, that might make perfect sense. So before we leave this, let's use this to calculate a Moran's eye, a spatial correlation, and let's make note of the value and let's see how that value changes as we change weights matrix. So let's close this, and Geoda will keep open this weights matrix until we define another one or load another one. So this is the active weights matrix, is the queen that we just created. So let's go here to space menu and look at a univariate Moran's eye. Spatial correlation. And let's click my favorite variable here, sales per capita. So this is how much liquor was sold per person in this county or independent city, keeping in mind that some of these counties or independent cities are dry and they do not have liquor stores. So there will be some zeros in there. So let's click OK. And here, using the queen weights matrix, this is very small, but we get a minus 0.0139. And again, what we can do is, this linking and brushing that we looked at earlier, we can select some of the points and it'll highlight those points. And so if we look up here, this is showing us areas that are high on both the individual region and the neighboring region. So this, on the y-axis, this is lagged sales per capita, and this is sales per capita here. So if they're both high, that's in this region. Let's look at the ones that are, say, high in one region, high in the neighbors, but low in the region we're looking at. So low areas, sorry, high-low, low-high. So we could look at low sales per capita, but high in the neighboring regions up here in this quadrant. And then low, areas where both an area and its neighbors are low sales. And so this is a very, very small negative Moran's eye. And as we see here, when you select some of the counties, it shows you the Moran's eye for the selected areas separately from the unselected areas. So you can see if any outliers are having any impacts. So if we select, suppose we think these are outliers down here, we can say, well, those selected ones have a 0 Moran's eye, so the line through them would just be flat, and the unselected are slightly positive. So these three are causing that negative Moran's eye we're getting of minus 0.0139. Without those 3 points, we'd have slightly positive of 0.06. So let's close that. And let's go to a similar kind of map, but a little different. Space, univariate local Moran's eye. This gives us a little bit more information. So sales per capita again, weights, the queens that we created. And let's tell it to give us a significance map, cluster map, and a Moran scatter plot. So here we see the same Moran's eye that we calculated before, the minus 0.0139. this gives us two additional maps to look at. So let's make those a little bigger here. So this helps us visualize those counties that are very high, high, very low, 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 high, high, low. So looking at the kind of extremes compared to just the nothing interesting going on here. In this one, it gives us an indication of significance. So which of these areas are statistically significantly different from the others? Let me tell you just a little bit about how Geoda does this. You see up here 999 perm. The way it determines statistical significance is by doing permutations, by randomly shuffling the data and seeing what kind of correlations we get. This is looking at small areas that are statistically significantly different from most of those random spatial permutations. So what we're trying to do is see if space matters. And if space doesn't matter, if we just randomly allocate these numbers, then we shouldn't see any spatial relationship most of the time. So we're comparing the observed spatial relationships to what do we get if we just kind of randomly shake up the numbers and throw them out on the map. So we see a few areas here that seem to have a statistically significant relationship where what we're seeing on the map is very different from most of the random cases that we're looking at. Now we can also go to this spatial scatter plot here, this Moran's eye scatter plot. We can right click and go to randomization, and you can tell it how many permutations you want to use to do a pseudo significance test here. So let's do 999. Might as well, it doesn't take but a second. And so this tells us that when it did these 999 permutations, it gives us a pseudo p-value of 0.434, which is not shocking, not surprising that it's so high, given that the Moran's eye here is so close to 0. And you can rerun this if you like, and you're going to get a pseudo p-value pretty similar most of the time. So let's just record one of these results. I'll record it in my Word document over here that I'll make a PDF and post, and let's compare to what we get with the other contiguity matrices or weights matrices we create. All right, so we'll come back to that. Let's go ahead and let's look at the difference when we create a rook weights matrix here. So I'm having a problem with clicking create. It's just not working. So I might have to close it down and try again. So you guys let me know if you have the same problem here. Open it up again and let's click weights, create, and let's use FIPS again. Rook. Precision threshold. So this is asking us when two shapes meet at a point, how precise do you want this idea of a point to be, which is technically going to be 0 length of the border between the two. So set the threshold to bridge the gap between disconnected polygons, or yeah, sometimes you'll see a weights file where the polygons don't actually touch right at a point like that. So that's an option. Let's see what happens if we just leave that blank. And again, we could include lower order neighbors if we wanted to here, but let's just do a standard rook, create, and let's add the word rook to the name so we know which file that is, since we already have our queen. Okay, so now let's look at our connectivity map here real quickly and see how this looks different. In most cases, it doesn't look like it makes a huge difference, although there are some cases where you can see a county maybe just to the right here. I mean, I can't quite move my pointer, but these two, if we were using queen, might be neighbors, but they're actually not under the rook. So there are going to be some cases where some counties are not neighbors anymore. And if we look at that histogram, we probably are going to see fewer neighbors than we used to. So this histogram is going to be shifted to the left now, since there are going to be some cases where you're not a neighbor because you just meet on a corner, and queen would count that and rook does not. And so again, we can click here and see which of these, let me just close that, see which of these have one neighbor. Sorry, we need to have this green one up in order for that to work. One neighbor, two neighbors, etc. So again, I encourage you to actually look at this and think about it whenever you're making your weights. Let's go and do our Moran's eye. So let's go space, univariate Moran's eye. Where is our variable? Sales per capita. And use the rook. And since we've got some counties selected, it's going to automatically break them into those two groups. So here we see a minus 0.013, which is not a whole heck of a lot different than what we saw before. Let's right click and let's do the randomization here with 999 permutations. And we see a pseudo p-value almost the same as before. So at least with this one variable, with this one map, we're not seeing a huge difference between the queen and the rook. But again, I didn't see a huge difference between who were defined to be neighbors between those two. So let's just make a note of this and let's go on and define a different kind of neighbor structure. Okay, so let's close this down, close this down. Let's see if we run into the same problem we did before with trying to create another weights matrix. No, here it's allowing us, so we have to select our weights variable here, our ID variable. Let's do a distance-based weights matrix. Just a warning here, guys. Most of the time, your map files, especially over large areas, are going to have longitude and latitude as the way that it's being mapped. So these geographic coordinate systems. You need to know with your map what kind of coordinate system it has. Is it being mapped based on longitude or latitude, or is it being based on a plane-based Cartesian coordinate system? How can you tell the difference? Well, this is something where you might have to go down the hall or call somebody to ask them, or do a little bit of Googling to see what kind of coordinate system your map is under. The most common kind of maps are either going to be longitude and latitude, where instead of a Euclidean distance here, you want to use an arc distance. So an arc distance means over the surface of a sphere, but sometimes you'll get maps, especially for smaller regions, say just one state or a part of a state, where the file will be in what's called a state plane coordinate system. A state plane coordinate system is a Cartesian flat rectangular coordinate system, not based on longitude and latitude. And in that case, you'd want to use the Euclidean distance. Now, if you use Euclidean distance, and I'll try to add a link to the video here where I talk about the difference between Cartesian coordinate and Euclidean distance and arc-based distances, you need to know that they're very different, have really very little to do with each other, and you can't just throw in a square root of x1 minus x2 squared plus y1 minus y2 squared. That kind of Euclidean distance formula is not going to work correctly. Automatically, it's going to use the x and y centroid, and the threshold distance here, I told it miles. The threshold distance is the minimum distance that you can use, given your map here, where you won't have any islands. So it looks at all the distances, and since you're not allowed to have islands, this suggests the minimum distance is about a little over 47 miles. And you can set this threshold distance to anything you want, where what this means is, what is the cutoff? So if I set this to 95 or 99, or you can actually just type, say, 100 in the box here, what I'm telling it is any two regions that are more than 100 miles apart, don't count them as neighbors. And this goes back to my comment before. You don't want to set this threshold to the max, where everybody is a neighbor to everybody else. You may or may not want to set it to the minimum. At the minimum, you're going to have at least one region with only one neighbor. Let's set it a little bit higher than the minimum here at 50, just to see what happens. Let's click Create. Now, when we save this, again, instead of the gal file, we're going to get the GWT file that has both the neighbor and the distance information. Again, give it a name to where we can remember what we did. So distance 50. And that tells me that we set it's a distance-based weight matrix, and we set that threshold distance to 50 miles. I should probably put miles here to remind myself that it's not kilometers, right? So save. Now, let's look and see if this changes our Moran's eye at all. So let's go to Space, Univariate Moran's eye, And here we get a slightly positive. Wow, all these are pretty close to 0. This is kind of boring. Maybe we ought to try a different variable. Actually, you guys try some different variables. And I'm asking you guys, play around with the data, play around with these different weights, and please report back to me anything interesting that you find. And maybe if I get enough interesting things that people find, I can make a follow-up video and we can look at some of those things. I'm sorry all these are turning out to be pretty close to 0 here, but let's do our randomization and just see what kind of p-value we get. So we're getting a p-value of about, a pseudo p-value of about 0.221. Let's record that and let's just do one more to see if we can get any other kind of interesting result here. Okay, so let's do something crazy to try to get a different result. See, now when I click create, it's not working. So let me close it down and reload. So let's create a weights matrix that's k nearest neighbors. So the ID, let's set to FIPS again, k nearest neighbors, and let's set k equal to 2. So this is just going to look at the centroids, Euclidean distance, and it's going to find, again, I don't like k nearest neighbors because to me it doesn't really make a whole heck of a lot of sense saying that the only thing that matters is the distance between the centroid of this county to the centroid of that county. I mean, what does that have to do with anything? Anyway, so we're finding the two closest based on distance between centroids. And just to try to get something different, I think probably 2 nearest neighbors is probably not enough in most circumstances, but again, use your best judgment. Create. So this is, again, a GWT file since the distances are being recorded here as part of the file. And I'm sorry, my handout was wrong. The k nearest neighbors, I think I suggested earlier in the video, would be a GAL file, but it saves it as one of these GWT files. So let's do 2NN. Save. And let's just see what kind of results we get here for our Moran's eye. See if we get anything interesting. Sales per capita. And so here we're getting a Moran's eye that's larger, about minus 0.05, and let's see if this is statistically significant, since that's what's all the rage, right? So randomization, 999 permutations. No, not statistically significant, even though it is a much larger Moran's eye than we had before, and still negative. So I'm going to do a couple more of these off camera, and then we'll compare the results to see if how we specify our weights matrices matters. So here are my results of playing around with it. And so if you're interested in p-hacking, of course, you can torture the data until it confesses. Lesson, if you try enough different weights matrices, you will certainly find what's probably not really there. So we have some negative Moran's eyes, positive. The comforting thing is that most of these spatial correlations are very close to 0. So the farthest one away from 0 in absolute value is this 0.0536. Not statistically significant with that pseudo p-value based on randomization though. But I did find 3 that have very, very low p-values here. One positive at 0.0165, and one negative, and another one here that is about 0.04, between 0.03 and 0.04, that has a very, very low p-value here. So basically, as you can see, at least when it comes to spatial correlation, Moran's eyes, that the choice of the spatial weights matrix does appear to matter. Again, we're not getting wildly different Moran's eye values, but when we're looking at, a couple of hundred counties here, say it's around 230 or 240, even small values, it's possible to get a small statistically significant p-value. So this video is entirely too long. Let's do one last thing, and let's just look at the structure of these weights matrices here, or these weights files that Geoda saves. So here's one of the .gwt files, and it has a header row which tells us there are 234 different regions. Here is the name of the shape file that we were using, and here is the name of the row identity file here. So this says 37, this is the state, this is the county or independent city name if it was Virginia. So it says that this was my 2 nearest neighbors file. So there's going to be 2 rows for each county showing its 2 nearest neighbors. And then here are the distances, and these should be in miles, but this does not appear to be miles. So the Geoda documentation page says that the third column with distances in the .gwt file is only used to determine whether a point is within a distance band or not. And it's not a distance. I can tell from looking at these, all of these numbers here are between 0 and 1, and the distance between these county centroids is definitely going to be more than whatever this number represents in miles. So I'm not sure what this means. And I checked a few of the GWT files, and I'm not sure what this is. Geoda does say that they row standardize, and I assume that for the K and N, they would all be, say, 10 nearest neighbors. All the entries would be weighted at 1/10. For the 2 nearest neighbors, it would be 1/2. So I'm not 100% sure. So these .gwt files, even though they do have some information here that's somehow possibly related to distance, be aware it's not a distance. Now, when we look at the gal files, the structure is a little different. So the header information is very similar, but here it has each region. It says how many neighbors does that region have? 4. And then it lists in the next line which those 4 neighbors are. And here this region has 6 neighbors, and then in the next row it lists what those 6 neighbors are. So the gal and the .gwt files have very different structures. Now when you go to use these in R or in MatLab or in Stata, there's always going to be some kind of command that you should look for in R, MATLAB, Stata, and Python. They all have a command that is something like readgal, or it might be read.gal or something like that. Just Google it. You'll be able to find some information on this. If you have any questions or just can't find anything, you can send me a message and I'll try to point you in the right direction. But I know that at least in these 4 platforms, that there are some built-in functions that someone has written or another to read these in, at least for gal files. Be more careful with the .gwt files. You cannot use these to create inverse distance weights. However, there are some functions I know in R where you can read in the shapefile. So the most important package in R is the spdep package, and with spdep you can read in shapefiles and you can define lots of different weights matrices, including inverse distance weights. Although I have not done that and used those myself, later on we'll do that in R. But for now, if you're just starting, I think the best thing to do is just create your weights matrices in Geoda. At least when you're starting, you can see what's going on a little more easily. In the next video, we're going to go ahead and we're going to run some spatial regressions in Geoda just to get our feet wet. It's a good place to get started just to kind of see what happens, but it is definitely not where you want to stop. And I hate to make this analogy, but I will. It's a good place to get started, but it's kind of like running ordinary least squares regressions in something like Excel. It'll do it, but it's limited. You can't do all the things that you need to be able to do, and we'll discuss that in the next video. So join me for that. Please like this video if you like it. Please give it a thumbs down if you don't like it, and please leave questions, comments, and other feedback in the comment section below. Thank you for joining me.